In this video, I will go through several examples that review the basic rules of exponents. This video in no way should replace the discoveries and patterns that you've been noticing in class, and should be used simply to supplement and help you review the concept later on. Our first expression is 3 to the 4th times 3 to the 5th. Our base of 3 with our exponent of 4 tells us that we have 3 times itself 4 times. 3 times 3 times 3 times 3. And our base of 3 with our exponent of 5 tells us that we have 3 times itself 5 times. This means that in total, we have 3 times itself 9 times. So I'll simplify this expression to be 3 to the 9th power. In other words, 3 times itself 9 times. We've noticed the pattern over the past few weeks that if we have the same base times itself, we can add the exponents because the exponents are simply telling us how many times we're multiplying that base times itself. The next example is negative 2 m to the 4th n to the 6th to the power of 2. This means that I have 2 groups of this entire expression. Negative 2 times m to the 4th times n to the 6th times negative 2 times m to the 4th times n to the 6th. Now we could write this out as negative 2 times m times m times m times m times n times n times n times n times n times n, and do that whole thing again, but we've already learned a pattern like our first example. So we know that when we see m to the 4th and m to the 4th, we can add those exponents and we'll actually have 8 m's in total. We also know that when we have n to the 6th and n to the 6th, we can add those exponents and we'll have 12 n's in total. You could write them out and count them as well, or visualize them in your head. Now I have negative 2 times negative 2, which is 2 to the power of 2, and we write that out as 4. So I have 4 m to the 8th, n to the 12th. Right away, I could see that I have an even number of groups, and we have a negative inside. If I have an even number of negatives that are being multiplied together, we will end up with a positive. So I know that my final simplified expression should be positive. Then I could take this exponent of 2, and since I have 2 groups of the whole thing, I actually have the shortcut. The pattern that I've noticed is that I could take this 2 and multiply it to each of these exponents, not to the base. It's only a coincidence that we got 4 over here. It's really 2 to the 2nd power because I take this 2 and multiply it with that 1. If you keep expanding, that is the best way to do this, but as we've noticed more and more patterns, it does become efficient to use these shortcuts. Our third example is the expression negative 2x over y to the 3rd to the 5th power. I've written the expression out 5 times so that you can see it, and we see again that we have negative 2 times negative 2 times negative 2 times negative 2 times negative 2. Since it's an odd number of negatives, we're going to have a negative in our final answer. Then we have 2 to the 5th power because we have 5 2's being multiplied by themselves. Then we have x to the 5th power because we have x times x times x times x times x. Oops, and all of these should have had a power of 3 on them. So we end up with y to the 15th in the denominator because there are 3 y's, then 3 more y's, then 3 more y's, then 3 more y's, then 3 more y's. So we have 15 y's in total. Again with our pattern, if we were to write in the exponents of 1, right above the 2 and the x here, then we could take this exponent of 5, and since we're going to have 5 groups of this entire expression, we know that that means we could take this 5 and multiply it to this exponent, take this 5 and multiply it to this exponent, and take this 5 and multiply it to this exponent. That's a pattern that we've noticed. So we have 2 major patterns. The first is that if we have the same base, then we can add the exponents because it's telling us how many times we're multiplying that base times itself. The second is that if we have parentheses, we can take our exponent on the outside and multiply it to every exponent on the inside, because it's telling us how many groups of whatever is inside we have in total being multiplied. Let's do a quick side note. If we had these expressions here, x to the 3rd times x to the 4th means that we have x times x times x times x times x times x times x. This is what we've just looked at. This means that in total I have 7 x's being multiplied, so I can add the 3 and the 4 to get x to the 7th. If I have x to the 3rd plus x to the 4th, that's already simplified. Those are not like terms. There's nothing more I can do here. Similarly, if I have x to the 5th times x to the 5th, that's x to the 10th, because that's simply 10 x's that are all being multiplied together. If I have x to the 5th plus x to the 5th, you guessed it, those are like terms. We typically write the coefficient of 1 in front of here to help us, so that's 2x to the 5th. I don't want us to forget what we've learned earlier this year and in 7th grade. The reason why we're able to add exponents in the examples we've been doing here is that we are multiplying these together. An exponent is just a shortcut to tell us how many times we're multiplying that base times itself. Let's look at 2 final examples and 1 final rule. If we have x to the 3rd over x to the 6th, we have the same base here. Our base in both cases is x. In the numerator, I have 3 of those x's, and in the denominator, I have 6 of those x's. I can divide the numerator by x and divide the denominator by x and cross one of them out in both locations. And I can do that 3 times because in the numerator, I only have 3 x's in total. This will leave me with 3 left over in the denominator. We looked at this pattern together in class, and we came up with the conclusion that if we have the same base, we can subtract the exponents and figure out how many x's, or whatever our base is, are left. In this case, if there were originally 3 in the numerator and 6 in the denominator, if we cross off the same number from each location, or divide by that base, we'll end up with 3 left over in the denominator, because we started with more there. We came up with a shortcut that we could subtract our exponents, but really the operation we're doing is division. We can look at one more example together. In this second example, we have 4 over 6. We know that that simplifies to 2/3. We also have x to the 4th over x squared. That means that I have 4 x's in the numerator and 2 in the denominator. So when I subtract, I'll end up with 2 x's, and those 2 will be left in the numerator. If I wanted to see the y, I would do this out. I split my 4 to be 2 and 2, and my 6 to be 2 and 3, so I can see that I can cross off a 2 in the numerator and the denominator if I divide both by 2. That won't change the value. Then I can also divide by x in the top and bottom, and a second time. That leaves me with 2/3, and that leaves me with x times x in the numerator. That concludes this review video. I hope it was helpful in helping you remember some of the patterns that we've noticed. It should, again, in no way replace all of the discoveries and practice that we've been doing in class. It's simply a summary of the patterns we've noticed and a good tool to use as a review for later in the year or if you are absent.